So in the last video I talked about wanting to take a velocity vector and dot it with the normal so that we can get the portion of the velocity vector that is in the direction of the normal. And then we need to add that twice to the velocity vector. If I take this vector and I add it to 2 times this white vector, its projection, let me do, I'm running out of colors. Let's do yellow, even though yellow is hard to see. If I take this white vector and negate it, I get a vector pointing this way, and if I times that by 2, then I essentially get 2 of those. And if I take the green vector added to 2 times the white vector, which is the yellow vector, then my resulting velocity vector would be like that. And that's the new velocity we should have coming off the wall. In fact, let me just move this velocity vector. I'm going to draw it right here. And if my drawings are good enough, you can see we're coming into the wall like that. We should be coming out of the wall like that. And we call a normal vector, this red vector, it's perpendicular to the wall, and it's normalized, meaning it's length 1. But I didn't really explain or stress why I wanted to normalize the normal vector. And that comes again down to a dot b. Let's say this is vector a, as we've seen in previous videos, and the red vector, our normal vector, will be vector b. So there we go, vector b. And if I do a dot b, we'll do b in red, b, that's equal to the magnitude of a, magnitude of vector a, times the magnitude of vector b, magnitude of vector b, times the cosine of the angle between them. And we've seen why we want the cosine of the angle between them, because that's how we do our projection. We're looking for that adjacent side of the triangle. Well, I don't want both the magnitudes in this equation. Recall that I'm trying to project vector A onto B, so I need to get rid of B, and the way I get rid of B is change it to 1 by normalizing it. That's why I normalized my wall normal. And there's several reasons why normal vectors are normalized. We'll see in various videos following this one, especially when we get to graphics and physics. We used normalized normals constantly. But in this case, I want B to go away, and so I'm going to change B to a 1 by normalizing it. And so then I'll have the magnitude of A cosine theta. And let me draw theta here in white. Well, the magnitude of A cosine theta gives me this portion of the triangle. And then this would be the sine side of this triangle right here, if I was interested in the sine, which I'm not. I'm interested in the cosine, so we can flip that vector around. So all we need to do, it's real simple. Take our velocity, dot it with the normalized normal, and we've seen how to do dot products, and then add that result, twice that result, to our velocity, and that will bounce our ship off the wall. So I'm going to clear all this off, and let's actually get to the code and do that. Recall we have this handle boundaries function where we were figuring out if we were colliding with any wall, and of course we were using the dot product there, but at that point we were only worried about the sign, positive or negative, of the result, not necessarily worried about using that result to project on anything. But now that we know how to bounce off the wall, let's see if we can make that happen. So I think we're done with this Q debug here. And then any collisions, I'm not worried about any collisions. If we have a collision, then we will handle it right here. Later we will see that detecting collision and handling collision is best done in 2 steps. But for now, I think we're fine just saying, hey, if the dot result is less than 0, then we're going to deal with it by using that simple formula I just showed in the beginning of the video, by taking our velocity and adding twice the projected value of it against the normal. So before we had the normal vector, and I actually want to normalize this now. So on the end here, after we do the perp counterclockwise in the xy plane, then we'll say, hey, give me a normalized version as well. And the rest is pretty straightforward. Ship velocity gets ship velocity plus ship velocity, dot that with the wall normal. Okay, but again, recall that the dot function returns a scalar when we were taking that velocity vector and it was approaching the wall like so, and we're trying to dot it against the wall normal here. Well, the dot product, it does give us this projection, as I said before, but it only gives us the length or the magnitude of that projection. What we have to do to actually get a vector out of that instead of just the length of a vector, I've been drawing vectors in all the videos, but to actually get a vector instead of just the length, I have to take that length and multiply it against the normal. So say this looks like a value of 2. Say the dot product gives us a value of 2. Well, 2 times the red vector back here, the red normal, will scale that out by 2. So the dot product, yes, it does a projection, but then we have to reapply that scalar result against the normal to actually get a vector out of it and not just a length. So then we'll multiply that against the normal, and that gives us the direction. But again, we don't want to just add the ship velocity dot the normal. We want to add -2 times the ship velocity. Okay, again, recall I'm taking the red vector and I want 2 of these, so then I'll add the velocity vector to that result, and that'll give me my new outgoing velocity, which if I move the screen vector over here, our new outgoing velocity is like so, exactly what we want. Let's run this and see if it actually works. That's a lot of videos for such a little bit amount of code, but hopefully you get the idea. Let me make this as square as possible. And we'll fly around and hit the wall and bounce. Let's see if we bounce here. Bounce, bounce. That looked pretty good. That looked pretty good. Bounce, bounce. Very cool. So there we go. We're bouncing off the arbitrary wall. Let me see if I can. Yeah, that's a little better. Ooh, tight there. Okay, and again, we're only using the center of the ship's position. Did you see the ship grab that line and kind of jitter a little bit? I'm going to address that in the next video. Most of the time it'll be okay, but once in a while it is going to grab the line and jitter, and we need to fix that.